Oh, I didn't hook this up yet. So I guess I had to do this before I start going on about how this looks in Canvas, but I can't remember if I mentioned last class or not, but on Canvas, so let me make sure this is recording. So on Canvas, I kind of created these two new, they look like assignments, but they're really just placeholders because everyone's highest or lowest exam could be different. So it just kind of, if your highest grade was exam 1, it puts that grade in there. If it's your highest or lowest grade was exam 1, it puts that in here. Kind of weights them using the 2 higher weights for the exams. So it's essentially assuming that your first 2 exams were your best exams, right? So if you didn't do so hot on one of them, it's going to kind of worst case scenario, right? Like if you don't do as well in the final. Every other thing is kind of weighted, and it's been up there for a while. The one thing I will get updated, the grades are going to be a little off. Each one of these assignments counts the same, even though they have a couple different points. So what I will be doing also is uploading a new, it looks like an assignment, but it's really just kind of what's the average of those 3 connect homeworks right now. And we have that 4th one up there yet, but since it's not due, I don't have that factored in, okay? Any other questions before we kind of jump into material? I want to make sure I mention that. Okay. And I won't give you guys another online quiz this week, so kind of get the weekend off. I would start working on that Connect assignment though, since we kind of went through a little bit of material. You can start to, after today, you can kind of start to chip away at that. So we did, this matched pairs, we're just trying to get at within people differences, like within the same person before and after. We then kind of started to transition to, well, what about these factors like that might have influenced income or whatever the example was? So we did this ANOVA. So we're going to go back a little bit and mention something that we talked about before, which was the correlation coefficient and covariances, right? So we kind of talked about, if these things are positive, that tells us that X and Y are kind of, as X goes up, so does Y. If they're negatively related, and as X goes up, Y goes down. And there's some measure of the relationship between 2 variables. So a lot of what we've done up to this point, right, other than this week, is looked at just one specific variable, not thinking about how it's related to another variable. So we're going to do, and I say it's review here, we're going to do some linear regression. And that's basically what we'll do for the rest of the semester. So we're going to be interested in the relationship between X and Y, these 2 variables, right? The goal is that eventually we can predict Y given some X value, right? So because we have a good understanding of what the relationship is, right? Maybe it's like years of education and income. If you tell me the years of education someone has, I can give you a pretty good prediction about where their income will be, right? So, and then you tell me, if their education goes up by a year or 2, what do I expect the change in their income to be? So what we're going to do is we're going to have this kind of equation where Y, right, is a function of X, right? A linear function, a nice, easy function, right? So we'll have some constant, right? Regardless of if you have 0 years of education, you can go out and get a job and earn some income, right? And so there will be some constant, and then B here kind of represents the relationship between X and Y, right? This is, kind of math, I won't say 101, but it goes back quite a bit, right? So anytime I see an increase in X, I could tell you what the change in Y would be. So the question is, how do I figure out what B is, right? How do I know what that relationship is between X and Y? That's eventually what we want to get to. How can I statistically estimate the relationship between these 2 variables, okay? Because maybe if I have another year of education, my income only goes up by, it's a big difference if it goes up by $1,000 or $10,000, right? So some terms that I'll start using, right, is this Y variable that we're interested in predicting is what we're going to call the dependent variable, right? It depends on X, right? So it's a function of X, therefore it's dependent on X. That makes X the independent variable, right? So X is what we're using to try to predict values of Y. Okay? The tool we're going to use is called regression analysis, or every time I refer to kind of linear regression or just regression, what I'm really talking about is the statistical kind of procedures of predicting what that relationship is between X and Y, okay? So if we think about more broadly what we're doing, before we get to I'll show you a little bit of the computational stuff, but like I said, once we have the background, it's mostly going to be interpreting some results that we see. So if I have my X and Y variable, and I kind of create this scatter plot, right? This is going way back to like week 1, week 2. If I tried to draw a line of best fit through this data, right, I would kind of see that it's downward sloping, right? Well, if it's downward sloping, what would the value of B be? If I have a downward sloping line, that means as X goes up, what's happening to Y? It's going down. So that value, which just represents the slope between Y and X, would be negative. Yeah, right? As X goes up, right? As X increases, Y is going down, right? So therefore we know that B is going to be negative. Right? It's also going to allow us to predict if you told me, look, if I knew the values for A and B here, like let's say A is 10 and B is 5, well then if you tell me that X is 13, I can plug 13 into this equation and get a predicted value of Y, okay? So that's kind of the general setup of what we're trying to do, right? We're trying to get these good estimates for A and B so that we can start to predict values of Y. So A, kind of if we're thinking about visually, and like I said, this is just review of some stuff you learn a pretty basic kind of math course. A is going to be our intercept, right? Because if X is equal to 0 here, well, 0 times B, doesn't matter what B is, 0 times anything is 0. And so when X is 0, that value of A is going to be our intercept of our line. And then the slope of this line, right, is just B. As we go up 1 unit in X, how much does Y change, right? That's kind of our interpretation of the slope, right? As X goes up by 1 unit, what is the change that we see in Y? Now, in this scenario, it would be a negative change, right? So it could be that a 1 unit increase in X causes Y to go down by 5 or down by 30, whatever it happens to be. But that's kind of our general interpretation of this. Okay. So we can see a bunch of different relationships, right? If I looked at a scatter plot like this and I try to draw a line of best fit, this is going to tell me that as X goes up, and nothing really happens to Y. Y is kind of unaffected by changes in X in this scenario, right? The data is kind of all right around the same area. Now, if I drew a line of best fit through this data, looks like it would be kind of upward sloping, which means that as X goes up, Y is also going up. So I would have a positive relationship. So in these scenarios, what would the value of B be here? Approximately 0, right? As X goes up, if there's no change in Y, then it would have to be B is pretty much 0. And then in this scenario, B would be positive, right? And that's what, or greater than 0. That's why we call it a positive linear relationship. Here, there's no relationship. And then that first one I showed you, once again, that would be kind of our negative relationship, okay? So that's what we're going to start out with. Eventually, we're going to get to where we can start to understand nonlinear relationships. So like this one, right? If I try to draw a line through it, it's kind of hard to figure out where it best fits the data. But if I was drawing a line that was curved, you could draw a curved line that really fit the data pretty well, right? So we'll call these kind of nonlinear relationships. We could see concave, we could see convex, but we're going to hold off on that discussion because that's something we'll do later on, right? First, all we want to do is understand these linear relationships, okay? So we have kind of this equation for the relationship between X and Y. But the issue is, if you tell me that somebody has, 16 years of education, yeah, I can tell you a predicted Y value, but for any one person, that's going to be off, right? On average, it'll be pretty good predictor of the average, but for Bill Gates or someone, it's not going to be very good prediction, right? So for what their actual income is. So we're going to have this epsilon, right? This error term. You can think about it as E or epsilon, whichever is kind of easier, but it's going to represent the error that we would be making with our predictions, right? So I can predict someone's income using these estimates I come up with and however many years of education they have, or for any one individual, it's going to be a little bit off, and how much it's off is this epsilon, okay? So when we come up with these predictions, we can't factor in this epsilon. We can't observe, right, the individual's kind of error term, right? All I can observe is whatever data I have on this X variable, which is maybe just their years of education. Right? So when I come up with these predictions, we'll call this Y hat, because it's just an estimate. Just like we were doing with sample means, we only have an estimate for what this Y value will be for the individual. What will we be missing? Well, we'll be missing whatever their error term is, right? Excuse me. So we've got kind of Y and Y hat, right? Y is the predicted value that we've come up with once we have the estimates for what A and B are. Y, just regular Y, is the actual income of the individual, right? So we could predict their income, but we're going to be off a little bit from what their actual income is. Okay? So if I try to think about this, if I kind of substitute some things in here, we'll notice A plus BX, that's just Y hat. So Y is equal to Y hat plus the error term, or the actual income is equal to the predicted income plus that individual person's kind of error term. Right? So how can I actually find, I can use this information to find kind of what these A and B values are, right? Well, if I think about this, if I have this data, right? And actually, I think instead of doing this on the slide, I'll actually do this one kind of using the board here. So if I had my scatter plot, right? So if I had this data, right, and the scatter plot looks something like this, if I come up with a line of best fit that best fits this data, well, the equation for this line, I was just calculating what Y was by that equation. Right? That's how I was coming up with kind of my predicted Y values. If you tell me an X value, so maybe this is the X value I'm interested in, I can plug it into this equation and come up with the predicted Y value. Well, that's great, but for any one observation, so let's say I'm looking at this observation right here. Right? Well, notice the predicted, if I'm looking at the X value for that particular observation, if I predicted what Y would be, it's going to be on the line. That's the predicted Y value. So you kind of think about it as, here would be the predicted Y, but here is that individual's actual Y value, right? What is the difference between them? Well, if Y was equal to Y hat plus this epsilon term, the difference between Y and Y hat is that error term. So this difference between your predicted Y value and the actual Y value for that observation represents kind of your error, right? So how do I know where this line is? Well, I can draw it and eyeball it, but to get the, once I have this line, there will be an actual A and B value such that it would be exactly where it's at, right? Well, how do I come up with what is the A and B value that gives me this line that kind of perfectly fits my data? Well, it's essentially going to be the line where we're making the fewest amount of errors, right? If I draw a line up here, if I think about if this is my predicted Y, I'm way off for every single observation, right? That's a terrible best fit line. What we're wanting to try to do is get a line such that the total errors that we're making for every observation is as small as possible. It will be the line such that if we were to calculate epsilon for every single term, for every single observation, that we've minimized what that total number of errors is, right? Because this line, the total errors is gonna be huge. I'm gonna have a ton of, if I sum up all the epsilons here, it's gonna be massive. But with this line, it's gonna, when I add up all those epsilons, it'll be kind of the lowest that I could get of any line, kind of linear line that I could draw up here, right? Now, we've got some issues. One being, well, if we were just to add up the epsilons, what's the issue with that? Well, here, right, the actual Y was greater than the predicted Y, so my epsilon would be positive. But if I had an observation down here, right, now the actual kind of Y is below the predicted Y. So if the predicted Y is higher, well, now my epsilon is negative, so if I add them up, they're just going to cancel each other out. So maybe I just think, okay, I'll just take the absolute value, right? I'm adding up kind of the total like absolute value of errors. But we're actually going to do this very similar to the variance. Because not only do we want to count any error, whether or not it's above or below the prediction, right? We don't care if it's above or below. We still messed up. We still have a wrong prediction, right? So we not only want that absolute value, but we want to really penalize errors where we're really far off. So similar to the, like let's say this was the data, but I had one observation that's way up there. So the way that we choose the kind of optimal A and B value to get our line of best fit will actually over-penalize those really bad outliers or those really bad errors, right? So similar to the variance, we'll take that difference between the actual y and the predicted y and we'll square it. Right? So what we're actually going to do is minimize the sum of, we're adding up all the errors between y and y hat squared. Right? Very similar to kind of what we were doing with the variance there. It's just now it's not the deviation of the observations from the mean, it's the deviations of the observations from this line of best fit, okay? So, you know, I kind of have this in here, maybe it's a little bit easier to see, but I kind of want to go up through the up on the board, but you can see here, now I've got an error term that's positive because the actual y is above my predicted y. Here I've got kind of, oops, the actual y is below the predicted y, so I'm going to have a negative kind of error term there. So I kind of already mentioned what we're going to try to do is minimize all of these errors that we're making squared, add it all up, right? The sum of the squared errors, okay? Now, if I were to write this out, and don't write all this up. This is just math to kind of give you a little bit of an idea of what's going on with the proof. So I can plug in, I have an equation for y hat, sorry. It's just a plus b times x, right? If I'm going to choose the A and B value that minimizes this formula, right? Oops. I could take some derivatives in respect to each one of those things. Once I have those derivatives, I set them equal to 0, and then I can kind of, two equations, two unknowns, I can solve for what A and B should be. I don't want to do that by hand. That's annoying. And we'll talk about later, like what if we have multiple variables in here? It'd be a lot of work, right? So, I already showed this slide. Hold on. We don't need this again. There we go. So you kind of take these errors. Oops, why did I repeat those? Yeah, it's the same thing, right? We're trying. I think I added this in because I forgot it. We're minimizing the sum of the squared error terms. We rewrite the error terms as y minus y hat. So on, you know, take derivatives, set them equal to 0, solve for A and B, right? So if we do that, you could actually work through the math and rearrange that these are going to be the two equations you can use. Now, I'm not going to make you use these equations. I don't think we'll end up having kind of time next week. I might show you how you could do this in Excel because, well, if it's just every observation minus the average for this x variable, I can put that in one column. Every observation's y value minus the average y variable, put that in another column. Multiply those two columns by each other, add up that entire column in Excel, do kind of a similar thing down here with the denominator. We could break this down and actually work through it. Now, the thing is, why mess around with this if we have built-in functions in Excel that will do all this for us, right? We don't want to have to do all the computation, and so I'm going to skip all this because we're not going to ever kind of use this unless I show you an example, right? But we're going to actually use Excel to kind of do all this work for us, right? It's going to go through every single observation. Remember, when we're looking at those scatter plots, every single observation is like a row in Excel. It'd be individual 1, in their income and their years of education. Next row, individual 2, their income, their education. So what Excel is going to do, it's going to go through every single observation, right? And kind of plug it, basically do all of this math for us, okay? So behind the scenes. So we already did this last class, but we need to get that analysis tool pack in there so that we see the data analysis under the data tab. So that's the same steps as I showed you to add the ANOVA. So let me just kind of show you what that looks like. So I put up 2 data sets, right? So usually kind of I default this to putting it on another sheet, but you can put it on the same worksheet if you want to, right? I specified where I wanted to put the output. I'm just going to put it right here next to the data so we can look at it. So it gives you kind of all this data. We'll talk about some of this, but for right now, what we're just going to focus on is kind of this first column, which is coefficients, right? So coefficients is just another word, like a fancy word of saying the predicted A and B values, right? So if I think about when I have this equation, we'll refer to as whatever the kind of output gives me as the predicted values for A and B, right? Those are the coefficients for my constant, right? We'll call this as kind of our constant, and then a coefficient for the relationship between X and Y, okay? So once we have those coefficients, we can essentially kind of figure out where that line of best fit needs to be, right? And, you know, once I have that linear regression tool in Excel, it's pretty easy to kind of get that output instead of doing all the work behind the scenes, right? And we'll talk about later, a lot of these other statistics that Excel calculates for us are also very useful. Right? So here's our kind of estimates for what that value for the intercept or the constant is, and then the value for that slope between SAT scores and GPAs. Right? So if it's 0.0019, let's think about maybe kind of how we can interpret that, right? So 0.0119, what we're really saying is, when I was trying to come up with those predicted values, for this was 0.00119 times, and I'll actually write our values in. We were trying to predict our Y variable was GPA, and our X variable was SAT score. So I now have kind of the slope, and I forget, what was the constant or the intercept there? I also have the value of 0.663. Okay. So I now have those two values. So if I wanted to put this on a graph, right? With my Y variable is GPA, my X variable is SAT score, I could think about, I could go through, plug in 0 here. So my intercept is right here at 0.663. And then I could just kind of continually plug in slightly higher SAT scores and get the corresponding predicted GPA and map out my entire line of best fit. Now, because that slope is 0.001, what we're really saying is if I went from an SAT score of 0 to 1, right? How much would my Y value go up? Only by 0.0019, right? So if I added 0.0019 to this, and I'm drawing this way out of proportion, but it'd be 0.6649, right? Just add 0.0019 to 0.663. Right? So I would know that that point would be here, and I could go through and do that and build my entire line of best fit. Right? So if you think about kind of here, we're always thinking about how we interpret that coefficient or that slope is if I were to see a 1 unit increase in my X variable, how much does my Y variable increase? Well, it increases by whatever that slope coefficient is. Okay? Does that make sense? Any questions on that? Now, this seems kind of small, right? 0.0019, but why is that effect so small? Because I would think that SAT scores, if I do better on the SAT score, I would also predict that I would have a higher GPA once I get to college. So why do you think that's so small? Think about the units. 1 point higher on the SAT score, it's not that much higher, right? Like, it's like not a very big increase. What we can start to think about are things like this. Well, if the predicted GPA, right? Sorry, actually, I'll do it this way. If the effect of 1 unit, kind of 1 point on the SAT score, is 0.0019, well, what if I got 100 points higher on the SAT score? Well, it would just be, this is the effect of every 1 point. The effect of 100 points would be 100 times whatever that slope coefficient is, right? And then we get something like 0.19, which 0.19 in terms of how much higher your GPA isn't insignificant. I mean, it's a decent little move, and that's only from kind of 100 points higher on the SAT score, right? You can think about, I mean, it could be 200 points higher, and we would see twice that, right? And you have to remember, SAT scores probably aren't the only thing that impacts the GPA, right? But that we set this up, so we're just trying to understand just the relationship between the SAT score and the GPA, right? So, you know, if you plug in like 1600 in here, right? Well, you would think, well, I should get a prediction of 4.0. Well, not necessarily, right? Because here you're just trying to understand the relationship just between GPA and SAT scores. Okay? Other things would have impacted as well. Right? Okay, so once we have this output, we can start to think about a couple other examples, and we can kind of just look at the output now and try to interpret it, right? So I had this data, which was the reported income of an individual and the number of days they reported using marijuana each month, right, or smoking each month. So I've got 5,000 observations. This was kind of younger individuals, and this was quite a while ago. This was like 79. So, you know, this is not adjusted for inflation. So that's why we kind of see a much lower income there. So all I did was, and this is a little bit different output that I might sometimes show you. So I'm only going to ever kind of expect you guys to use Excel, but there's other data packages like Stata and SAS that kind of present the data in a different way, but it's still all the same statistics. So I just want to get you used to kind of seeing kind of different different outputs here, but it's still the same idea. So I'm going to what we call regress, or use this regression analysis, where my Y variable is income and my X variable is the number of days that someone used marijuana. Don't worry about this. I was just doing it for 1 year. So here's kind of that equation that we're trying to estimate. Here's our coefficient estimates for the constant or the intercept, right? Those two words are interchangeable. And the coefficient on that X variable, which was the number of days I used marijuana each month. So it's kind of, presented a little bit differently, but it's still the same information. We could think about here, if somebody uses marijuana 1 more day each month, their predicted income goes down by $253, right? Like, this is how we always interpret these coefficients, right? I can show you the visual. It's a 1 unit change in that X variable. Before, 1 unit was 1 more point on the SAT score. Now, a 1 unit change is 1 more day of using marijuana each month. Right? You could probably come up with, what if you used it all days? So like multiply this by 30, and that's how much your income takes a predicted hit if you're smoking marijuana every day, right? So, it's pretty, it's useful to be able to interpret things like that to know the relationship between 2 variables. Right? And kind of notice, like, even if someone's using it 0 days a month, so 0 times negative 253 is 0. So the predicted income, kind of like where you would start out at, not using it at all, is right around 32,000. Okay. Like I said, kind of older data, but still interesting. Okay? So that's how we would interpret this slightly different looking output. Right. This kind of a reminder, kind of our constant we can think about as the intercept, and then here it doesn't kind of label it as the coefficient. It tells you this is what was the name of the X variable, and here is the coefficient on that variable. Right. So we kind of already did this interpretation, but just kind of a reminder, it's always just in general, it's a 1 unit increase in your X variable causes whatever that slope coefficient changes in the predicted Y variable. Okay. So what about the constant? Well, the constant, I kind of mentioned the math of it, but the way in general we always interpret the constant is going to be if the X variable is equal to 0, right? If they didn't use marijuana, 0 days out of the month, what is their predicted income? So it's if the X variable is equal to 0, the interpretation of the constant is if that X variable is equal to 0, this is the predicted value of Y, okay? Or income in this example. Okay. So that's the interpretation part. I think that's relatively easy, right? Just kind of once we get that down, Excel or these other statistical programs will do it for us. But we then want to think about, we have to remember, just like when we were trying to figure out what the population mean was and we found a sample mean, the way we found these coefficients was from sample data, right? So we really only have like sample coefficients, if you want to think about it that way, right? We have just estimates of what these actual relationship or what these actual values are. And so based on the data, there's going to be a certain amount of variation that we have as well in the estimate that will impact, well, you can almost think about it like this, right? We could think about it, since we've already done something similar, you can think about it as, I'm going to be coming up with estimates for what that slope is, and they should be centered around what the true relationship is between those variables, but there's going to be some standard deviation or variance associated with this distribution as well. It's going to depend on, just like before, the variation that we see in the data. So this isn't going to be exactly right, but you can kind of think about it as, you think about it as the, you want to think about this as like the variance that we would have, right, in that actual relationship between x and y, and like divided by n. That's not mathematically exactly what it is, but if it's easy to think about, what matters is the variation we have in the data, but also the sample size we take still really helps us, right? Because if we take higher sample sizes, reduces this distribution, then we know that kind of the estimates we get for the coefficients are more likely to be right around whatever that true coefficient is. So it's the same kind of idea of what we were doing before. It's a little more complicated than that, but if we think about it that way, that's fine. So we need to get some measure, right, of what the variation was in this estimate, right? So we could do 3 different types of tests, and here it says that actual is the true population slope kind of coefficient, or the relationship between x and y. Is it greater than this assumed true value, less than, or not equal to? Now, we're never going to be actually looking at this, because any test that we're going to run, we're always going to be assuming that that slope coefficient is not equal to or equal to, and the value that we're going to use is 0. I mean, there are cases, I'm sure, that you don't use 0. I wouldn't expect, I mean, that's kind of a higher level thing. I wouldn't expect any time kind of being in kind of undergraduate course, you'd really ever look at examples where you don't want to test for whether or not that coefficient is equal to 0. Sorry, what you want to test for is that it's not equal to 0, so you're assuming it is equal to 0. And this makes sense. We're starting off stacking the deck against ourselves just like we were in prior hypothesis tests, right? I'm going to assume there's no relationship between these 2 variables, right? If I can find strong enough evidence that gives me a high enough estimate, right? So what we've assumed, I just said, is we're always going to assume that that true population relationship between x and y, we're always going to assume that it's 0, right? So now when we find these estimates for the slope coefficient, if they're far enough away from that assumed true value, then we can reject that value. But if we reject that value, what we're saying is we found strong enough evidence such that we can reject that there's no relationship between these 2 variables, or we found evidence that there is a relationship between these 2 variables. Okay? So anytime we do that linear regression tool, it's always kind of using that null and alternative hypothesis, which is we'll assume that that slope coefficient is equal to 0, right? Or think about the alternative is that it's not equal. So we're always doing a two-tailed test, essentially, right? So if we start out assuming there's no relationship, well, we don't care if we find evidence the relationship is positive or negative. We just want to know what that relationship is, if it's anything other than 0, okay? You know, I'm not going to make you actually kind of go through and do this test by hand, but we could, right? And so one thing we'll notice, if we go back here, right? We've got some test statistics that are given to us from the output. Now, we could calculate them by hand, but if the output is going to give them to us, then why worry about it? And so we're going to have test statistics here, right? We're also going to be given p-values, right? So we've got test statistics and p-values here. We can start to make rejection decisions, okay? So to go back here, all the test statistic is, the way that it's being calculated, is it takes whatever value that you see for that slope coefficient and subtracts the assumed true value. Well, we just said the assumed true value is always going to be 0. So it's just taking that slope coefficient and dividing it by something called the standard error. Okay. Now, you're always going to be given that in the output. You're given the coefficient, and you're also given the standard error. So if you wanted to, you could go through and calculate the test statistics, even if it didn't show them to you. So I'm not going to focus on this too much because you're not going to have to calculate this yourself. But the standard error is really coming up with some measure of variation that we see in the data in terms of what the difference is between each individual's kind of Y value and the predicted Y value. Right? So notice in that output, we had the coefficients, we had the standard errors. If we're assuming that all the coefficients are 0 here, then it should just be that the way we get these test statistics is my coefficient of -253 divided by that standard error of 48, which would give me that test statistic of -5.2. So simply divide your coefficient by your standard error, and that would give you your test statistic. But, you know, like this Stata program and Excel will give you those test statistics right away. They'll also tell you your p-value. Okay. So, what do I want to do here? We got 2 more minutes left. I think we'll kind of revisit this. Hopefully I'll figure out how to get the regular data analysis back here on my Excel. But, you know, if we look at kind of Excel's output, just as a reminder, it gives you the test statistic and it gives you the p-value as well. So one thing that's going to become really important with this p-value output is notice it's scientific. It's like e to the negative. So this is essentially 0, right? This p-value is essentially 0 on these. But it's really easy to look at these and think 2.3. But remember, p-values are between 0 and 1. So anytime we see this e to the negative, we've essentially got a p-value of 0, which means we can reject. So here, between SAT scores and GPAs, right, what are we rejecting? We're rejecting there's no relationship between GPAs and SAT scores. In fact, we're rejecting it at really high levels of confidence, right? The p-value is pretty much 0, so we can reject at any level that we wanted to. Okay. All right, well, sorry we ran into that roadblock today, but we got some good discussion on linear regression. We'll pick up on it next class and then start to talk about, well, what if we think that more than one thing impacts that Y variable, okay? So start working on that Connect homework, at least for a few of the problems now. You might be able to get through some of them based off what we did today. Other than that, I will see you guys on Monday.